its implementation, its fast execution, the FFT, the fast Fourier transform. And if time permits, I'd make some comments on the discrete cosine transform, and it also can be implemented by the FFT. So it's equally fast. So actually, this is pretty much the final. We're at the transition now toward wavelets. So the previous lecture was about Fourier transforms. This one focuses on the discrete case, and it's still in the applied math book. Section 5 is the FFT solo, and chapter 4 has the material on Fourier transforms in general. And of course, you know that I'm going to give a matrix expression to the main ideas. The main ideas being the transform, its fast execution is a factorization, and then convolution. The central ideas of the subject, and familiar to many of you. You probably could get the formulas right more often than I. And then the second lecture today will really begin the move into the wavelet book, discussing filtering. Actually, in the same lecture, I'm going to have filters in the time domain, in the frequency domain, in the Z domain. So filters, the basic tool of signal processing. Okay, so here's certainly a basic tool, and I've written up, so we have to decide how many samples we have, capital N. And sums will run from 0 to n minus 1, typically. Indices will go from 0 to n minus 1. So we have n samples. And we want to find n Fourier coefficients, discrete Fourier coefficients, that reproduce them. So the number, this complex number, e to the 2 pi I over n, comes into the everywhere here. So let's just be sure we've got that number pinned down. In the complex plane, let me draw a circle of radius 1, the unit circle. So of course this is the real axis. This is the imaginary axis, so that number right there would be I. And now where is the number W? Is it on the circle? Yes. Everything of modulus 1, of magnitude 1 is on the circle. This is an e to the I, theta. So theta, the angle, is 2 pi over n. So where does that go? 1/nth. I mean, the whole angle is 2 pi. And we want theta to be 2 pi over n. So we go, let me take n to be 8, let's say. So that would be e to the 2 pi I over 8. So that's W. Maybe I should really call it Wn to indicate that it's determined by that number n. Okay, and now you're going to see powers of W, so let's just be sure we've got those down. Where is W squared, for example? You notice I don't write the rectangular, the real and imaginary parts. I could, cosine and sine of 2 pi over 8, because when you're multiplying numbers, this polar form is much, much better. And when those numbers are on the unit circle, so that the polar r is 1, then there's absolutely no question it's superior. So r is 1, we're just adding angles when we multiply. So if I square that one, what number do I get? I get I. It doubles the angle. That angle was 2 pi over 8, 45 degrees, doubles to I. So then the cube of it would be here. Add another. When I take the cube, I multiply by another e to the 2 pi I over 8. I add that angle once more. Here's the fourth power. So this is W8 then. There is W8 squared, which is the same as W4. And that's the big deal, actually. The fact that W8 squared is the same as W4, and in this example, I. So I'm eventually, in the fast Fourier transform, I'm going to be interested in the half size transform. So this is anticipating what's coming. Here's n equal 8. Here's m equal 4. And the point is that Wn squared is Wm. And that's the trivial but all-important link between the transform, the 8x8 transform, and the 4x4 that we can take great advantage of. Okay, I better finish the powers of, so there are 8 roots. There are 8. This is like a tongue twister. There are 8 eighths. Do I spell that with a, did I do that right? I'm too close to it. Okay, 8 eighth roots of 1. The equation is w to the 8th minus 1 equals 0, and like every polynomial of degree 8, that has 8 roots, and they're all very nice. And so we've identified those w's. Okay, so now this may take a little looking, but it's completely analogous to say this formula for the discrete Fourier coefficients would be completely analogous to the Fourier series case, where instead of our finite number of y's, 8 y's, we would have a function. And this let's just write down what the Fourier one is. So what's the kth coefficient of f of x? We take f of x times e to the minus I kx, right? dx. And possibly we divide by a 2 pi. And I guess what I'm hoping is that you think that this is maybe somewhat, even more than somewhat, analogous to this one. Here's our data. Here's our, if you think of what W really is, and W bar, of course, makes it a minus I. And I could even do better, Bob Nichols is contributing to the course webpage proof of the Poisson formula, and he puts a 2 pi up there and cleans up this part. But let me stay there. Anyway, one can connect the discrete with the continuous, but we don't really have to. The discrete stands by itself, and I want to express it as in matrix language. Let me express this one. So this is saying that the vector y, y0 down to yn minus 1, is some matrix. This is the reconstruction formula. This is the formula that gives the coefficients. Also, the 2 are so easily flipped that probably you would see both interpreted as analysis and synthesis. But I'm thinking of this as synthesis. Use the coefficients to reconstruct the y's. So somehow there's some matrix there multiplying those coefficients. C0, C1 to C, well, let's call it 8. Well, 7 in this case. So, right. Since n is 8, we have vectors of length 8. numbering from 0 to 7, and we have an 8 by 8 matrix there. It's the Fourier, I'll call it the Fourier matrix of size 8. And I just want to ask what it is. What are its entries? And this equation is supposed to be a copy of this one. I don't know if you like to see sums and indices, or if you like to see the matrix kind of, well, it's pretty equivalent, because what are the entries now of this Fourier matrix? They're the things that multiply this. So this is row J multiplying CK hits column K of the matrix. So those are the entries of the matrix. There. F. So let's write out a few. What's the first row of the Fourier matrix? All ones, right? All ones is exactly. Thanks. Because J is 0 in the first row. Okay, so it's all 8 ones. And the first column also. Why is that? Because K is 0. Okay. I see I'm going to get crowded here to get an 8 by 8 matrix in, but let's get the second row and column in, or depending how we want to count that. If we count that as the 0th, maybe this would be row 1. What are the entries along that row? So now J is 1. So the entries are 1, right, omega or W squared, cubed, and finally 7th. Right? There are these numbers. 1, right, sitting around the unit circle. And now to really pin it down, what's the next row? J is 2 now. So we're squaring them, so we have W squared, W to 4th, and it's symmetric, of course, actually, so this is going to be down to W to 7th this way, W to 4th, W 6th. Well, let's really pin it down and find the last, what's the last number here? W to what power is sitting in the lower corner there? 49? Yeah, seems right. We're in the 7th, n minus 1 squared. Right, 7 times 7. We're at the end of our rope here, W to the 49th. But, of course, W to the 49th is an alias for some other smaller power of W. What would it be in that particular case? Just the first power, is that right? W to the 49th is 1? That's interesting. So W to the 8th is 1. W to the 8th power is 1. So W to the 48th, yes, right, 48th power is 1. And W to the 49th, yeah, is just W. Good. Okay. So anyway, W to the JK. Those are the entries. All right. And what's the inverse? Well, you might say, wait a minute. This is a full matrix. No zeros at all. How do you expect to find the inverse of an 8 by 8 full matrix? Oh, and a little thought is coming to my mind, which we will find the inverse safely. And, of course, it's got to be revealed by this formula, because this is the formula that goes back from the y's, connects the y's back to the c's. Can I just throw in a comment here? Because I like to mention also some things that I think are not as clear as you would think. I mean, the whole world has studied this matrix, and you guys have seen it and so on. Its eigenvalues well, I know what its eigenvalues are, and we can see. So this is a digression, because the eigenvalues of the matrix don't play a big role in the theory, but they have a role. They have to. So it turns out the eigenvalues, it turns out that the fourth power of this matrix is the identity. If I've normalized correctly. Actually, a better, sort of more symmetric normalization would put 1 over square root of n there and 1 over square root of n there, and then that would give us a 1 over square root of n. I usually don't include that in defining the Fourier matrix, but we could. So if we do, then we've normalized this matrix so that its fourth power turns out to be the identity. So that's pretty nice. Now, carrying on this digression, just because some of you will know all too well the DFT formulas, what about the eigenvalues of this matrix? If the fourth power of a matrix is the identity, what does that tell me about its eigenvalues? What are the possible eigenvalues of a matrix F? It could be 1. The possible eigenvalues are 1 and minus 1 and I and minus I. True. And no others, right? No others. Why is that? Let's just see why that is. Why? Suppose we had an eigenvalue and an eigenvector. Suppose so. This is the reason then. Why? Reason why? If fx equals lambda x, I'll apply f, and again I would have f squared x equals, what do I learn from f squared x? It would be lambda squared, right? Because it would be lambda fx, but the fx is another lambda, so I'd get lambda squared x, and then let me jump to f to the fourth x. I would learn that that was lambda to the fourth x. But now, if I have this incredibly special situation where the fourth power has come around to the identity, then this would be x. So I learned that lambda to the fourth, so lambda to the fourth has to be 1. And if lambda to the fourth is 1, those are the only 4 possible lambdas. Okay, and so first of all, we have 8 by 8 matrix, or actually we have n by n matrix for every n. This is true. These are the 4 eigenvalues. So what puzzle could remain here that I'm going to ask you about? Yes. It's true for any n. Any n, yeah. It's true for any n. And that is, I agree. Yeah, so that you might try to prove that. I guess maybe f squared is minus I, is that right? Anybody remember? If f squared is minus I, then we're certainly got f to the fourth nailed down. I think maybe f squared is minus I, and f fourth is I. Yeah. Yeah, that should be fun to prove, but let's take that as something we can check, and then that tells us what the possible eigenvalues are. So what other questions could I ask? I could ask about the multiplicities, exactly, and there's an answer for that. You know, let's see if. In the 8 by 8 case, since 4 goes evenly into 8, I suspect that they're each multiplicity 2, but my memory doesn't, you know, this isn't a problem I really know about. But I think, and then otherwise, there's, you know, then if it's n by n, then n and 4 doesn't go evenly into n, then we've got some, you know, we've got to make the count right, but it's known. What isn't known, in a satisfactory way, at least as far as I could tell, and I just had occasion to look through various papers, is what are the eigenvectors? we've got the I mean, this seems amazing to me. We've got the eigenvalues. We know their multiplicity. I mean, that is checked out. But what's a nice description, but straightforward description of the eigenvectors? And that of an independent, the right number of independent and should be orthonormal eigenvectors. So I'll just leave that as a puzzle. And I cannot swear that in some paper the answer doesn't appear, but I read through a whole series of papers on this topic, and they all had a sort of shot at it, but none of them were really satisfactory. So there you, I mean, if Legal Lab comes up with a good description of the eigenvectors, will be, or you will be, deservedly famous, I'd say. Okay, so that's a digression on this short bit there. Because it's not the eigenvectors, it's the inverse that we really want. Okay, so how could a matrix be easy to invert? Let's put this square root of n in for the present here, as I've done now. Okay, so how could it be easy to invert? Well, actually, one way here is to say, well, what does that tell you about the inverse of f? It's f cubed, right? The inverse of f is f cubed, but we don't want to deal with the cube. We really want to see that the inverse of f, so here's the main point, that the inverse of f is the conjugate, complex conjugate. Of course, so that symbol, by that symbol I mean replace I by minus I every time you see it. Okay. So that its entries, the entries are the complex conjugate of these. So its entries, and I'm putting in the square root of n now, are the complex conjugate of those, which is w bar to the jk. I just take conjugates. Now, can I just be sure on this picture that I know where w bar is? So where is w bar, the conjugate of w and its powers in the complex plane? Are they on the unit circle? For sure, they're reflected in the x-axis, exactly. So this will be w bar, right? It will be e to the minus 2 pi I over 8. Right. So it'll be the same as w to the n minus 1, but w bar is much cleaner. Okay. All right, now why? Why? So I'm claiming that, really, why? The point is that f is, well, so what I'm claiming is that, yeah, I guess I'm just claiming that f bar times f gives me the identity, right? It's just as simple as that. I just have to check that f bar, if I take this matrix and it would be more familiar to have f bar transpose, and it's symmetric, so we really do have f bar transpose. Yeah. So I'll put a transpose up here. I was going to say in light letters, but if I do it in yellow, it'll be visible. The transpose has no effect because the matrix is symmetric. But what kind of matrices have this? Do we have a name for matrices like this? Well, you take a matrix F, and you take, what's a matrix for which F transpose F is the identity? Unitary is the word we use, especially when the matrix is complex. We use the word orthogonal matrix, and certainly have in this course, for the real case. But and we could stretch that word, but it's better to use the word unitary. That's a sort of signal to the mind that complex numbers are in there, and you not only, it's not F transpose F in the complex case. As always, one of the factors should be conjugated. That's just a fact of life in a fact of complex life. It's conjugate one of the factors to have the proper analogy with the real case. And now just tell me what identity. So this, what if I write that out? What does that tell me? Let me multiply. Let's take a typical row. Shall I take row? Yes. To get the diagonal. Yes, but why do I get 0 off the diagonal? So the two questions: why do I get 1 on the diagonal? And that should be not too hard. So let's do on the diagonal. Suppose I take this guy with this one. Oh, but one of them is conjugated. So on the diagonal. So on the diagonal, let's take a typical case. 1 times 1, W times W bar, and so on. W seventh times W bar to 7th. What does that sum equal? Yeah, it's n. Right. Every term is 1. So it's 1 plus 1 plus 1 n times, and I divide by the square root of n twice, and I get the 1 on the diagonal. So that part is good. Now, what about off the diagonal? Okay. So now, if I'm off the diagonal, what am I looking at?
Off the diagonal, you end up getting all the sums of all the powers, don't you?
Let's see what we get. Let me take an example. What example should I take? Shall I take the W squareds times the W's, just for the heck of it? Yeah, let me do that one just for the heck of it. So I'd have 1 times 1, because all the rows starting with 1, and then say W squared times W bar, and then W fourth times W bar squared, and finally, I guess when do I quit? You see what I'm doing? I'm taking this row times this column conjugated. Right. 1 W squared, W fourth, up to W to the 14th maybe, times 1 W bar squared, W bar to the 7th. And what do we claim this is without thinking why first? We're hoping for a 0. The favorite right-hand side of all mathematicians, right, is 0. Yeah. So why is that 0?
This is the sum of all the powers. If it's sum
Yes. Okay. Now, why is that? One W will cancel a W bar, right? And 2 W's will cancel 2, and 7 W's will cancel 7. So this is in disguise is really 1 plus W plus so on plus W to the 7th. In this particular row and column that we chose, we got those numbers. And why do they add to 0? The picture is one way. Yeah. How do you
Just take the equation W to the 8 minus 1 and factor out W minus 1.
Right. That's right. So this is really W to the 8th minus 1 divided by W minus 1. Which we could see if I multiply up by there, I'll have the W to the 8th. I'll have a W to the 7th, but then there'll be a minus W to the 7th. It's like telescoping. And then finally the minus 1 with a 1 doesn't telescope. And yeah, so this would be, that's a formula that one picks up and then drops in high school, right? The sum of a geometric series. It's just a geometric series. And why is it 0? Well, because W8 is 1. So this is This is 0 over W minus 1, and of course that's our big 0, right? Okay, and similarly, if I had any of these other row time columns would give me 0 in a similar way. Okay, well, so we have really, I think that's really not a bad idea to actually check that this is true. And then, of course, we've identified, and the transpose didn't matter, we've identified the inverse matrix, and then we put it here in the formula. The inverse is just the complex conjugate, and that's what's the analogy in the Fourier transform case? You remember there's over an infinite interval, you remember there's a minus e to the ikx, minus e to the minus ikx in one direction and e to the plus ikx in the other. It's exactly like this, yeah. Okay. What about the fast Fourier transform? So, two steps are kind of remarkable for a full matrix. One is to be able to invert it, to know right away that its inverse is just its conjugate. That's pretty remarkable, but pretty old. The other highly important step was the fast Fourier transform. So I'm ready for that now. What's the fast Fourier transform going to be? Okay, so the fast Fourier transform. So we have this matrix Fn. The n by n, this is the n by n, of course, Fourier matrix. And it's full. But it's possible to factor it into matrices that have a lot of zeros. And that's the key idea of the FFT, and the reason we're going to relate Fn to two copies. Let me leave enough space. So I'm going to factor this matrix into three factors. One will have a lot of zeros. One will be half zero, Fm, two copies of the half-size transform, and one will be really simple, just a reordering, a permutation matrix. So before I write in those two pieces, let's see what the main point is. The main point is that I can connect the n by n Fourier matrix to two copies of the m by m one. And then half of that matrix is 0. I can do two m by m ones if I just do the multiplication out that way. Of course, I'm going to pay a price in whatever complexity is involved in these pieces. I might say that the 8 by 8 is a standard choice in image processing, and 8 by 8 is just about close to the borderline where, depending on what hardware you want to create, what the chip wants to do, whether you use this FFT idea and reduce to a couple of 4x4s, or whether you just go with it. You say, okay, I can do 64. I can deal with 64 non-zeros. But we're going to get down to well under 64 numbers. And, of course, for higher n, it pays off tremendously. Okay, so what are these factors? Well, these are the identity. This is the identity of size m is sitting here and here. And here is a diagonal matrix of size m, and here is its conjugate, I think. Yeah, so I have to say, what is this diagonal matrix? It's the matrix 1 w squared to w to the m minus 1. It's diagonal. And, or maybe it's just this. Maybe this isn't conjugate. It's just minus the thing. Yeah, I think it's just minus. Okay, and I'll come back to that matrix. This matrix is a permutation that puts all the even coefficients, 0, 2, this permutation, P here. P takes the numbers, the indices in the order that they come, and puts them in the order evens first, 0, 2, 4, 6, 1, 3, 5, 7. So it evens before odds. So in other words, this FM acts on the even indices, and this FM, this half-size transform, acts on the odd indices. I really should have, I mean, you know what I mean. So this is P. So the matrix has 1 in that position, 1 in that, 1 in that, 1 in that. That's the 0th, 2nd, 4th, and 6th. Then 1 in the 1st, 3rd, 5th, and 7th. That would be the 8 by 8. I'm a little sorry I jumped ahead to 8 by 8 here. But that's it. And there's the... why don't we, just to be, because this is the key. Can you tell me what it will look like breaking up? So, well, there's one more key idea here, and what is it? If I have, yeah, so if n is 1024, let's say, let's take that as an example, 2 to the 10th. I'm doing the FFT radix 2. It's actually the only one I know. Shmuel Winograd created by number theoretic tricks efficient FFTs of prime powers, prime order. Mine are these are the very opposite of prime, and these are probably the most used. So suppose n is 2 to the 10th. How many multiplications? How many multiplications would it take to multiply just flat out by the matrix F of this order? So the operation count would be what? And what's the number that we're trying to improve on? So if I just multiplied an n by n matrix by a vector, if I just did this or did this, and I've got how many terms have I got? N squared, right? Because I've got n terms in each sum, but then I've got n of these. There are n squared entries in the matrix. Okay, so I'm trying to beat n squared versus now, and what does the FFT lead me to? I'll try to. Okay, so this single step led me to half n squared, cut it in half, and I won't count that because those are just adds. And here is just an n over 2. It's just multiplying by, those both multiply the same, since they're in the same column, they both multiply the same lower half of the vector that's coming out here. So I just do one multiplication and then reverse sign. So you see a big saving. What's the next idea? Do it again. I mean, if there's any message in modern algorithms, it's recursion. Just repeat the same idea so that each of these would then factor into into a couple of F2s. If this is an F8, 2 F4s, then the next step we'll have 4 F2s, and if we really went crazy, we could go down to 8 F1s, so that in the end, this part is costing nothing. It's then the question is, how much do these parts cost? And how many of those parts are there? So this is n squared versus what? Yeah. So can you can you do the count for the Fourier, for the FFT? What is it?
N over 2 plus N over 4.
Let's see. We might, I don't know if we, well, that would be fantastic, because that would add up to n. Now, I think, yeah, and it looks deceptively that way, but I think we have each, I think this n over 2 shows up every time, because even the next time, these will be half as big, but there'll be, you know, so I think so it's n squared versus n over 2. Now, how many factors of those? 10, right, which is log n. So I'll put numbers in a minute, log to the base 2 of n. So it's n log n. That's the famous thing. It's 1,024 squared versus, so n is 10, 5 times, oh, no, versus, yeah. Well, n is 1,024, and then the log is 10, as you said, and we even get that times 5. Well, boy, that's pretty amazing. And it really is true. Not only, you know, it's not a mirage that you, in place of 1,024 squared, which is 1,000,000 operations, we got 5,000. And that, you know, that's saving, it's a factor of 200 saved right there. And really, truly saved, because we get the exact answer, and it's stable, and it's hardwired, and it's very efficient. Very efficient, yeah. So, and you see how all that's, you see where that's coming from then, that you keep breaking this down, so you keep having more and more of these factors and more permutations. So if we could put all the permutations together into one single big permutation, which is called bit reversal. We can interpret the product of 10 permutations as a single permutation. Could I, just before I leave this, let's see, what does this factorization precisely mean for n equal 4 and m equal 2? Do you mind just if we, I hope the camera's got the lecture plan, and I've reached this far, and I'm going to move now to these. But let's just take the 4x4 one and factor it. So what's the 4x4 matrix, n equal 4? What is W? What's W for? So the 4x4 matrix is 1, 1, 1, 1. And what's W? I. The fourth root of 1. I squared, I cubed, I squared, I 4, I 6, I cubed, I 6, I 9. And the factorization is what goes in the middle factor. Let me put in the that, and that. And what goes in the middle factor? 2 by 2, right? The 2-point DFT twice. And what's that? 1, yeah, the row of 1s, the column of 1s, and minus 1. Minus 1, right. Minus 1. And another copy. So that's a reduction of the 4-point DFT to 2 copies of the 2-point DFT. So minus 1 is W. M is the square root. Okay, and then here we have the identity, 1 I, and 1 minus I. So I guess I'm risking my, I won't say my reputation, my memory maybe, on the fact that if you multiply those out, it comes out right. Well, there could be a factor 2 in this for square root of 4. I wouldn't be surprised. Oh, you're right. So I think that is right. Yes. So I didn't risk my reputation on the other one. Now I'm ready. I think that's it. Yeah. 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 Okay. I won't take lecture time to multiply that out and find out is there a factor 2. But anyway, you see the idea. And of course, we know that the DFT, the FFT, we can just call it. So it's a little. It took a little time to say what it does, but and I could draw a flow chart instead of a matrix factorization. But anyway, there it is. All right. Now, convolution. Cyclic convolution. So cyclic convolution means in goes a vector of length n and another vector of length n, and out comes a vector of length n. Same output. Normally if I had a polynomial with n coefficients, so I guess its degree is n minus 1, and I multiply by another such thing, what do I get out? Some higher degree, right? But now I want n numbers in this cyclic convolution. So it is like multiplication, but it's the polynomial is a polynomial in W. Maybe that's the good way to look at it. So let's see. So we got this inverse, okay. So here's convolution. Looked at one way. Well, and of course, there's a convolution rule that connects it with multiplication. So if I multiply y's by z's or something, then I'm multiplying a polynomial with coefficients c times a polynomial with coefficients d. Let me just think of multiplying polynomials. So suppose I have a sum of c k w to the k, and I want to multiply that by a sum of d, dl w to the l. Then these polynomials are of the degree that we're always interested in here. Okay. What's up? So I'm multiplying a couple of polynomials, which we certainly know how to do. But now W is not just a place-holding variable. W is this particular number. So that what happens when I multiply, say, suppose, let's take n to be 3. Let's take n to be 3. So I'm multiplying C0 plus C1W plus C2W squared times D0 plus D1W plus D2W squared. And what's the main fact about W? This particular number W, it's not just a symbol, it's a number. And what's the key fact about it? It's a root of 1. And I've chosen n to be 3 here, so it's W, it's the third root of, so W cubed is 1. Okay, what's the constant term? What's the constant term in the answer? Well, you would say C0, D0. But there's more to it. What else is there? The subscripts add to 3, right. We're working modulo 3. Because if the subscripts add to 3, then W cubed is just 1, and we've got a constant. So it's C1 times W2, D2, right? Because that's, and then C2 times D1. So that it's again, as with convolution in the last lecture, the key is the sum of the, but those all add to 0. 2 plus 1 is 0 now. What's the coefficient, now just to say, what's the coefficient of the W term? Well, we could see C0 D1, and there's add to 1, C1 D0, and finally, what's the other one? C2 D2, right, C2 D2, because that's W fourth, but W fourth is W, because W cubed is 1. Let me put that in yellow. Okay. And finally, we've got another guy here. This is the W squared term. C0 D2, C1 D1 is a W squared, and C2 D0 is a W squared. Good. Well, so what's the convolution then? It's these three coefficients in yellow parentheses. Those three numbers are the outputs from, so this is the convolution of these three numbers, C0, C1, C2, convolved with the three numbers D0, D1, D2, with n equal 3 as our count, three counts. So vectors, two vectors go in, and one vector comes out. This vector, now I'll just forget what they multiplied and just say, there's the first component, there's the second component, there's the third component. Don't need a comma. Okay. It looks a pretty tricky operation, right? And actually, how many, let me ask that same question again. If I wanted to convolve a vector of length n with a vector of length n, as here, and get a result as here, how many multiplications do I have to do? N squared. 9 in this case. Every C multiplies every D somewhere along the line. But there's a smarter way to do it, right? Well, 9 we could deal with. Modern computers can do 9 multiplications in a reasonable time. Let's go up to 1024 at least. So again, we're in the same situation. If our vectors are, if we're up to 1024 times 1024, then if we did it this way, we'd have 1024 outputs. Every one would involve 1024 multiplications and adds, and we're up to 1024 squared right away, and that's not the way to do it. So what's the good way to do? What's the good way to convolve a vector of length 1024 times another one? Use the FFT somewhere, right? So what's the idea then? We would use these. We would use the convolution rule, right? We'd combine the. So it's an end run. We would take those C's, put them in this formula, and find 3 Y's. We would take the 3 D's, put them in the same formula, and find 3 Z's. So right, this would lead us to, are you with me? We're beating n squared again. And we're going to do it the same way with the convolution. The convolution rule, and then letting the FFT take over. So this goes to 3 Y's. Y0, Y1, Y2. And these 3 go to Z0, Z1, and Z2 by by the DFT. This was a DFT. So how many operations does it take to do this? If I give you the C's and ask for the Y's, that's the FFT. I'm asking you to multiply by the Fourier matrix, and we know how to do that fast. And so we have to do that here, and we have to do it here. But now, what do I do next? Now, you see, here's the beauty of it all. I'm in the transform space. So in that space, this convolution becomes, shall I use MATLAB notation? Point in MATLAB notation. Point, star point, sorry. Star point. Is it, oh God, I'm revealing. Is it point star or star point? Okay, right. So what does that mean, that point? Do every element, do it element-wise. In other words, you get y0, z0 is the first component, y1, z1 is the second, and y2, z2 is the third. Big difference from what we had to do the convolution. This is just element-wise. So no cost. I mean, cost is n. And then what? Then we have to go back with one more FFT to the answer we want, C star D. C convolved with D, and yeah, that's a D there. Okay. So there were three FFTs: transform, transform, inverse transform. So three of these n log n's and one n. But of course, I mean, we saved an enormous amount here. If this was a factor 200 quicker, well, we had to do three of them. But we're way ahead. Okay. So that's convolution, the convolution. So actually, this is how you could, if I had two very, very long numbers, or if the computer had, suppose we're not rounding off at cutting off at 16 bits or even double precision. Suppose we're keeping full precision for algebraic coding or something. Then and then we have to do these multiplications in full. If I want to multiply a 128-digit number by another 128-digit number, well, it's a convolution, and I could use the convolution rule to do it. Yeah. Okay. What's remaining on my list for this lecture? Circulant matrices. I want to express this. I want to express that convolution as a matrix. What matrix is multiplying what vector to give that vector? It's nice. I'm happy that we see the three components of the answer. Now I just want to see it as a matrix multiplication. Some matrix is multiplying some vector to give these three. This vector of, I'll use the this is the convolution. Three components. You could delete the parentheses around them if you liked. Really, it's just three components. And I claim that that is some matrix of C's multiplying some vector of D's. D0, D1, D2. What's in the first row of the matrix? Well, it must be C0, C, yeah. What's the first row of my matrix? C0 should multiply D0, C1 should multiply D2, and C2 should multiply D1. So the row looks funny. I should have looked at columns. D0 multiplies what? What's the column? What's the zeroth column here that D0 multiplies? Well, D0 multiplies C0, C1, and where is it? C2, yeah. And then in the second one, D1 multiplies C2, C0, and C1. And then the third one, D2 multiplies, D2 multiplies, where's D2? D2 multiplies C1, right? C2 and C0. Oh, well, look. The pattern is, this is my circulant matrix. This is my circulant matrix times my vector. Gives the same result as C convolved with D. That's my point. That these matrices, a matrix of that type is a convolution matrix. And what do I mean of that type? I mean that down the you remember we used that word tuplets for constant diagonals, but this is constant diagonals modulo 3. The first diagonal is the same as the -2 diagonal. And the second diagonal is the same as the -1 diagonal. So this is a circulant matrix. Okay. It's a convolution. It's a cyclic convolution matrix. A convolution with wraparound, whatever adjective is most expressive. Cyclic, periodic, wraparound, those are all telling us that it's not 5 independent diagonals, because we don't want we don't have 5 independent things. It's 3 independent numbers there. The 3 components, C0, C1, C2. Okay. It's really valuable because filters in the next lecture this afternoon are going to be tuplets matrices. And you'll see, well, they could be infinite, so no wraparound. So I'll start the lecture with n equal infinity. So I won't call them circulants anymore. I'll just call them tuplets because the diagonals will go forever. But if we have a finite image, which of course we do, then there has to be some closure, and one way to close it is wraparound. Make it periodic. So this is the periodic version of a filter. This is a filter with wraparound. Any points coming to mind about that matrix? I guess I do want to ask you about one point, even though it's, as usual, my lecture is running a little over. That's a matrix whose eigenvectors I am interested in. That's a matrix whose eigenvectors are very important. And the beauty is that the eigenvectors are the same for every circulant. So there's a little world of circulant matrices of a given size, n, and its eigenvectors are everybody in the world in that little world has the same eigenvectors. So that's what I want to say the eigenvectors of C, of my circulant. We haven't really understood right now I introduce circulants just as a matrix vector shorthand to produce the convolution. But we see these matrices. The course has been, actually, so have we seen these matrices already? Almost, right? In those first lectures, the -1s, 2s, -1s. Well, but now did we see it with minus ones in the corners? Maybe in the notes we did. The periodic version. Yeah. Okay. What are the eigenvectors? 1, 1, 1 is an eigenvector. Good, good, good. I mean, good. All right. So the eigenvectors. Let me make a list of them. There's an eigenvector. 1, 1, 1. How does everybody? What's the eigenvalue? If I multiply this matrix by 1, 1, 1, let's just see. Yeah, sure enough, this is an eigenvector. Multiply by 1, 1, 1, and what do I get? So I'm really convolving, you could say, with the 1, 1, 1 vector. And what happens? Well, the eigenvalue is C0 plus C2 plus C1 times 1, 1, 1. Right? Right? Every row adds to this same number. Okay. And what is that number? Well, so I just now want to ask you to identify what we've just discovered. One of the eigenvectors and its eigenvalue are what? This eigenvalue is a column of my Fourier matrix. It's the DC term. It's the 1, 1, 1 column of my F3 Fourier matrix. And so this is going to be the point. The eigenvectors of C are the columns, are the columns of F. So F, the matrix F, contains the eigenvectors of every circulant. It'll diagonalize the circulant matrix. In other words, okay, so what's the, yeah, you have to, you know, let's just, this is so wonderful. Take a circulant matrix, multiply by its eigenvectors, and you remember this process with eigenvalues and eigenvectors? You take your matrix, you multiply by the eigenvector matrix, so that is nice because C multiplies the eigenvectors. Then you multiply by the inverse, and anybody remember what comes out of that process? This is for any matrix now with its eigenvectors there and the inverse of the eigenvector matrix. It's, what is it? It's diagonal. Yeah, this is diagonalization. And what do we, so it's the eigenvalues that sit on that diagonal, and those are, since those are little lambdas, we use capital lambda for the matrix. So this is diagonalization. So another way to say this is the Fourier matrix diagonalizes every circulant matrix. Different circulant matrices will have different eigenvalues, but the eigenvectors are always those same guys. So if I multiply one circulant matrix by another one, I just get a third one, and the eigenvectors don't change, and the eigenvalues just multiply. All right, we got the eigenvectors. Have we got like 1 minute here? What are the eigenvalues? Okay, that's, I don't know if I've given you enough to go on. Oh, well, let's find the second one. We got the first, yeah, well, tell me, what was that first? Yeah, so, right, C0 plus C1 plus C2, what is that actually? That's over here, isn't it, in some way? Where would I get C0 plus C1 plus C2 out of this? When J is 0, yeah. So this is, I guess I'm saying this is the first component of the DFT. We ought to multiply. What's the second eigenvector, or do we take this risk? The second eigenvector, or another eigenvector, let's say. Another eigenvector will be what? 1, yeah, W squared, yeah. And if I do that multiplication out, I hope I'm going to get a multiple of 1 W squared. I guess I said I would. So what's the multiple? Well, maybe maybe I just, yeah, do you see what that multiple would be? So, yeah. It'll be some y, somebody's going to say y2, and that's probably right. Yeah, it's, right? Yeah, just, okay. Sorry, I've gone blank here. What number do I put in? If this is true. It's something like, is it something like C0 plus C? It's the first.
The first row of the matrix times the column.
Oh yeah. Well, I knew there had to be a good way to look at it. Right. And since we're getting a 1 here, if I multiply that by this, I should get, yeah, that's what I have to put in here. So it's C1, yeah. So it's C2W, C2W and C1W squared. Okay, we're getting, yeah. Can I call this guy W squared? You don't mind if I give that a new name?
Switch the powers on your W's.
Yeah, I've got them right here, and it's just, it's just, now, let me write this in terms of W bar. Let's see, did I multiply C0, C2W, and C1W squared? Sorry? I'm not surprised that this is coming out a little funny because this is really C0, this is C2W bar squared. Right? W is the same as W bar squared. And W squared is the same as W bar. So it's coming out with the, there's a little switch between, a little conjugation happens in this. Don't let that spoil the end of the lecture. What's the main point? The main point is the eigenvectors are the Fourier matrices, are the Fourier matrix, and the eigenvalues are what? Are the DFT of C, but it might be the inverse DFT. We might be doing the W bar instead, and I think we are doing the W bar instead of the W. The textbook, I think, gets it right. But the main point is that, and do you see that this was our trick here. This was our trick. You remember our trick here that involved 3 applications of the FFT? Well, I've got 3 here to do. If I want to operate with C, let me just finish this thought here. This matrix C, I'll put the rest over on this side, is F lambda F inverse. Somehow, so if I want to do a convolution, that means I want to multiply by C. Instead of doing it n squared straight out, I do what? I take a Fourier transform one way or the other. I need lambdas, that's a Fourier transform. You see that each of these 3 I could do with an FFT? So there's 3 FFTs, and is an FFT in each of those factors. That's an FFT to multiply by F inverse, and an FFT to multiply by F. And where is the FFT needed in that factor, which is a diagonal matrix? It's to get the lambda. To figure out what that diagonal is, I have to do the FFT. So anyway, this is like a matrix fanatics way of seeing that a convolution, which looks like an n squared operation, can be done with 3 FFTs. So 3 of these plus 1 simple step. So really fast. Okay, this is quite a lot of symbols, quite a lot as I look at it, but probably quasi-familiar already. And I hope that these sections of the book, 5.5 and 4.2, would give you a reference to just sort of check it out, because we certainly did get a little twist here between W and W bar. Yeah, yeah. Okay, so let's break there and then start pretty directly with filters at